So thanks everybody, and welcome to this morning's webinar on maths, probability and ratio. They're not necessarily two topics that go directly together. It's not necessarily that you would always do probability and ratio at the same time, but there is some similarities between them, and we found that neither of them warranted their own webinar, but they did warrant going together, so that's why we're going to go through these. What I'm going to try and cover today is looking at what probability is and how you calculate it. And we're going to use things called probability lines and probability trees. And then we're going to move on to ratio. Again, look at what ratio is and how you display it, how you calculate it and show it. We're going to calculate amounts from ratios and ratios from amounts. That makes sense. And we're going to look at simplifying, expanding and comparing ratios. When we've run these before, these webinars, I've mentioned that there are two types of functional skills, the reform, which is the older functional skills, and legacy, which is the old one, and the reform, which is the new one. And you might be aware of which one you're on. Sometimes there is a difference between them. There isn't really for these. Probability and ratio come up in the old functional skills and the new one. Those who are doing the new functional skills will probably know there's part of your test where you can't use a calculator, and both probability and ratio could be in the calculator bit or in the non-calculator bit. But it definitely comes up in both tests, particularly ratio. You'll probably get 2, maybe 3 questions on ratio, maybe 1 or 2 if you're unlucky. You'll get 2 on probability. So they are quite key subjects. So probability is can be displayed in various ways, including pie charts. And what probability is ultimately, right? That's another bothering us. There we go. So what probability is ultimately is the likelihood or the chance of something happening. So it could be tossing a coin, whether you get heads or tails, rolling a dice, picking a card at random, a whole variety of things. It's the chance of something happening. And the way we work out and display or work out probability is we look at the number of ways that something can happen, and then that is over or divided by the total number of possibilities. I'll explain that when we do some examples shortly. So it's the number of ways something can happen against the total number. And we usually represent probability either a fraction, a decimal, or percentage. I've done fraction and percentage webinars before, and decimals come into both of those. So if you're not too hot on fractions or percentages and you didn't do those webinars, you may want to go back to those, and I can send you the recording, simply because some of the things I'll mention today were relevant to those. But we do tend to talk about probability, the fraction, and decimal. One thing I will mention on that is often in the questions in a test, it will say, what is the chance of this happening? Give your answer in a percentage, or give your answer as a fraction, or give your answer as a decimal. If it doesn't, it's sort of up to you what you give. You might want to give all of them. Percentage is usually one of the more common ways, as you might remember from the webinar. Percent means out of 100, per 100. So percent is a good way of looking at probability, because it's easy to compare to others if you've got percentage. Fractions and decimals can sometimes be a bit harder to represent. But if it doesn't say, it's up to you to choose which one it is. Fraction, decimals, or percentage would be okay. Personally, I usually go for percentages, but you don't have to. You also may be asked to display your probability on a probability line, which looks a little bit like this. And at one hand, you'd have something definitely not happening, maybe 2 or 3 lines in the middle where it could happen, and then something definitely happening at the other end. You may have to create this line to show it. If we're talking about decimals, something definitely not happening gets a value of 0, something definitely happening gets a value of 1, and in between would be 0.5. And if we're talking about percentage, similarly, you've got 0 is definitely not happening, 100% it's something definitely happening, and maybe the middle line would be 50%, as you're probably aware. So probability lines are quite useful in terms of showing probability and saying some of the tests, it will actually reduce those, work out the probability, and put your X on the line where you think it should be. So the first thing we're going to look at for probability is rolling a dice. Hopefully you've all come across a dice before and aware a dice has 6 sides to it. Just like that. So there's a number of things we could do in terms of a dice. First of all, I'm going to say, let's look what's the chance of getting a 6. So we roll the dice, and what's the chance of getting a 6? I said that the calculation for probability is the number of possible ways you can get something over the total possibilities. So the number of ways you can get a 6 on one dice is only one way. There's only one number 6 on a dice. There's only one way we can get 6. The total number of possibilities, the 6 sides to the dice, the total possibility is 6. So as a fraction, the chance of us getting a 6 and we're rolling a dice is 1/6, 1 over 6. If we do that, and if you've got a calculator, you're welcome to turn that into a decimal. All you do is 1 divided by 6, and that would give you a figure of 0.167. And to turn that into a percentage, we times it by 100, which gives us a percentage of 16.7%. oops, excuse me, 16.7%. So the chance of rolling a 6 on the dice is 1 in 6, 1 over 6, or 0.167, or 16.7%. All of those answers are perfectly accurate, perfectly good, and they show the probability of getting a 6. Next one we'll look at is what's the probability of getting an even number? Well, we're still out of 6 because there's still 6 numbers on the dice. But with the dice, we could either get 2, 4, or 6. So there's 3 ways of getting an even number. So our total possible ways are 3. So our fraction is 3 over 6. If you remember from fractions and simplifying, that's the same as a half. If we did 1 divided by 2, we'd get 0.5. And if we times that by 100 to give us a percentage, we get 50%. So the probability from a dice of getting an even number is a half, also known as 0.5 or 50%. And finally, an example. What's the probability of getting more than 2 when we roll a dice? Once again, we're still out of 6. We've still got 6 sides to the dice. I've said more than 2, so we're not going to include a 2 as well. So basically, you could get 3, 4, 5, or 6. So there's 4 different ways of getting that. Again, we can simplify that fraction to 2/3. If you're unsure about simplifying fractions, as I say, we did go over that in the fractions webinar, so please refer back to that. If I do 2 divided by 3, it gives me a figure of 0.667. And if I times that by 100 to give me a percentage, it gives me a percentage. Keeps doing that, right? It gives me a percentage figure of 66.7%. So the chance of a probability of getting more than 2, 2/3, 0.667, or 66.7%. Go back to the PowerPoint presentation, and I'll put those on here just so that when I send the PowerPoint out, you can see the figures. We can now plot this on our probability line. So some things we didn't do. The chance of getting a 7 is definitely not, because you can't get 7 from 1 dice. Similarly, the chance of getting more than 0 is definitely, because you're definitely going to get at least 1. So those, we didn't do those, but you could easily put those in if you had to. The chance of throwing a 6 was 16.7, so I've roughly put it about there. The chance of getting an even number was bang in the middle, 50%, so that goes there. And the chance of scoring more than 2 on a throw was 66.7. So again, it's sort of roughly around where that is. Usually instead of arrows, you put a cross on the line in terms of your functional skills test. So probability from that point of view is relatively straightforward. We've looked at the number of possibilities, the number of ways you can get something over the total number of possibilities, and we've either done it as a fraction or as a percentage. That's great for specific activities where it's got one outcome. So rolling 1 dice, or you could have rolled 3 or 4 dice, and it'd still be the same kind of outcome. What's more difficult is where you've got something that happens more than once, so maybe rolling 2 dice, or in the case I'm going to look at is actually tossing a coin. One way to represent this is what's called a probability tree. And these are really, really good to understand where probability is. You wouldn't necessarily have to draw one of these in the test. If you did, you can't do it on the computer, so you have to do it pen and paper, and rather than showing you working on the screen. But you might find this is a useful way for you to work out probability if you have to in the test. So I'm going to take the tossing the coin and the chance of either getting a head or a tail. Hopefully, if you think of a coin, you know one side's a head and one side's a tail. There's only 2 possibilities that you can get, either head or tail. And obviously, the chance of getting a head is 1 out of 2, and the chance of getting a tail is 1 out of 2, because there's 1 head and 1 tail. There's 2 in total. So the probability of getting a head is half. Probability of getting a tail is half. We then toss the coin again. So let's say we had a head first time, and then we get another head, or we toss the coin, we got a head, and now we get a tail. Similarly, we had a tail originally. Second time we could get a head, or we could get a tail. The probability is still a half for each of these, because the coin still has 1 head and 1 tail and 2 sides in total. So it doesn't matter whether you got head first time, it doesn't affect your probability of getting the head the second time or tail the second time. You've tossed it and then got that result, and then you've tossed it again and you've still got the same probability. So we could keep doing this as long as we want, as long as my screen will fit on. So we've got our probability of each individual occurrence. What we want to look at is what's the probability of getting a head and then getting another head. So we're actually talking up here. So we've got a head and then a head. Well, the probability of getting the first head was a half, and the probability of getting the second head was also a half. To work out the combined probability, what we do is we multiply these figures together. And again, if you did the fractions webinar, then multiplying fractions, what you do is you multiply the top line and multiply the bottom line. So our top line is 1 times 1, which is 1. And the bottom line is 2 times 2, which is 4. So the chance or probability of getting a head and then getting another head is a quarter, because there's no impact on whether you got the head first time as whether you get the second time. If we did head then tail, you'd see that's half and half, so that would be a quarter as well, as would this, as would this. And if you think if each of those is a quarter, if we added them all up, that would give us a whole, because we've got 4 quarters there. So this is a simplistic probability tree showing head, tail, and then whether you get head or tail or not, to work out the combined percentage. So if we want to work out head, then head up here, all we do is we take the first probability, multiply it by the second probability, and that gives us a quarter. And again, I could turn that into a decimal or turn it into a percentage if I wanted to. I'll leave it as a fraction. So hopefully that was relatively straightforward. A little more complicated now is where we do an event where the second outcome is dependent on the first outcome. And if I talk through an example, hopefully that will make sense. Excuse me. So let's take, we've got a bag, or a box in this case, that has got 3 red balls in it, and it has got 2 blue balls in it. And it's in a box, in a case, so you can't see them, and you're asked to pick a ball at random. So when you pick the ball, the chance you will get is either you will either get a blue ball or you will pick out a red ball. There's no other options in there. There's either blue or red. Remember that probability is the chance that something could happen over the total number of chances. So the chance of us getting a blue ball is 2, because there's 2 of them, but there are 5 balls in total, so it's 2 out of 5. The chance of getting a red ball, there's 3 red balls, and there are 5 in total, so 3 out of 5 is the chance of getting a red ball. We then pick again. And let's say we once again pick a blue ball. Now, one of the things here is we picked a blue ball in the first instance, and if we don't put it back, that means we've got 1 less blue ball in the back. So to pick a blue ball this time, our total possibilities are 4, and there's only 1 blue ball in there. So it's a quarter is the chance of us getting a blue ball. Chance of us getting a red ball, well, there's still 3 red balls in there, but now there are only 4 possible balls in there, so it's 3 out of 4. If we, let me just try and do my pretty picture again. Pretty's pushing it a little bit. So this time we chose a red ball, which means if we now choose a blue ball, there's 2 blue balls in there, and there are 4 balls in the bag, so it's 2 out of 4. That is actually a half, but we'll leave it at 2 out of 4 rather than causing any confusion at this stage. And the chance of me picking a red ball, well, again, there's still 2 of red balls now, and there's out of 4. So that's 2 out of 4, but also known as a half. So now, if we wanted to look at the possible probability of us getting a blue ball followed by another blue ball, let's go. So we're talking about here, blue ball and blue ball. You'll see our fractions were 2/5, 2/5, and 1/4. If we do 2 over, oops, sorry, on the pen. If we do 2 over 5, remember I said combine them, we multiply them, is 1 over 4. 2 times 1 is 2, and 5 times 4 is 20. So it's 2 out of 20, which we can simplify to 1 over 10. So the chance of us getting a blue ball followed by a blue ball is 2 times 2 over 5 times 1 over 4. That gives us 2 over 20, which gives us a total of 1 over 10. And again, I could turn that into a fraction, into a decimal or to a percentage. So rub this bit out here, give another example. Let's see if I can rub the orange circles out, because that might help. Will it let me? Ah, excellent. So this time I want to look at what's the possibility of getting a blue and a red. So if I get my orange circle again, the chance of me getting a blue and a red is obviously here's a blue and here's a red, so it could be here. Or I could get a red and then a blue. So that's here. If I do the calculations for both of these, my blue then a red is 2/5 times 3/4. 2 times 3 is 6. 5 times 4 is 20. And I can just actually simplify that down to 3/10. It will let me fit it on the screen. And if we look here, coincidentally, just because of the numbers we've actually got here 3/5 times 2/4 or half, which is actually the same calculation. 2 times 2 is 6. 5 times 4 is 20. So again, that's 3/10. So the chance of a blue then a red is 3/10. Chance of a red then a blue is 3/10. So if we add those both together, we will get 6/10, which again we can reduce down to 3/5. Jumped a couple of stages there, but the diagram has allowed me to do that. And again, we're in a test. You have as many bits of paper that you want to draw on and practice and things for. But by showing each possibility, by showing my probabilities for each one as I go. And when I get to the end of the tree here, all I've got to do is multiply two probabilities that I'd like, and that will give me the final answer. And then I can look at what I want. I can work out the answer for all of them, and then whatever the question asks me, I know. Or if the question just says, what's the chance of blue, then blue, I can do what I did first, 2/5 times 1/4. Go back to here. This is just a neater way of showing exactly what I've just shown. As I said, I will send out the recording afterwards and some practice questions. You'll be able to practice that. But hopefully you were able to follow as I was talking. So when you do come to practice, understand and say there is a difference in independent and dependent. The first one's independent because it doesn't matter what you got first time, you've still got the same probability of getting head or tail second time. The second one is more dependent because we've taken a ball out, so that affects our future numbers. But probability for each of them is still the chance of something, of how you can do something over the total number of possibilities. And that's probability. Any questions so far, Eamon?
I've just asked the question. Nothing's come through just yet.
Okay, well, hopefully people are still with us. I appreciate probability it can be a bit difficult. Certainly when we're talking about probability trees, there may be something you've never done or certainly not done since school or something like that. But as long as you follow that pattern, you're okay. And actually, probability in itself is not that hard. It's the number of ways something can happen over the total number of possibles.
Oh, it's not easy. I hate probability, I have to be honest. I found it quite. But okay, it's like I feel that I'm quite weak on this subject. So if I want to improve or if I need more, how many questions will be there?
Probability, usually one, maybe two questions. As I mentioned, those who are doing the new version of functional skills where you get half of the test is no calculator and half is calculator, you'll probably find one in each section. For those doing the older version of functional skills where you get calculator throughout, you'll probably find just one question throughout it, maybe two. And you may find they're combined, such as we've done there, or you may find that they are, I was going to say simpler, but they're straightforward, such as rolling a dice or picking something at random.
So it will be something that easy level? It's not, we're not going to be expecting something a bit more complicated than what you showed us.
What I've gone through, it won't be any more complicated than what I've gone through there. Obviously, I appreciate some of that is a bit complicated. And for those doing the newer functional skills, you may have to do some of it without a calculator, but which I know makes everything a little bit harder. But hopefully there shouldn't be anything harder than that. And what we will do, as I said, is we'll send out some practice questions afterwards, so you'll get a chance to practice and see exactly the kind of questions you will get and how they'll be worded.
Okay, all right. I always hated probability since I was at school, so
it's not uncommon. I mean, one of the things we do.
Fraction, but probability is my weakest point. Okay, so can I do something, Paul? So when is the new version coming? So when is the deadline for the old?
If it's okay, I'll go on to ratio, then I'll come and answer that question at the end, if that's okay.
Yeah, okay, all right.
Brilliant. So looking at ratio is different to probability. Ratio is about the relationship between two numbers or more than two numbers. So it could be making a coffee and how much milk you've got compared to espresso, whatever it might be. So it's the relationship between figures. And we normally write a ratio as an amount of one thing, a number, and two dots, a colon, and then an amount of another. So A colon B. And what it means is A compared to B, or A in comparison to or related to B. So once again, what I'll do is I'll talk some examples here. There's about 2 or 3 elements of ratio that you need to know, but hopefully by talking through examples, I'll simplify them down. So the first thing we'll look at is making a glass of orange squash, orange juice. So to make that, you need some orange cordial and you need some water. And we're going to write the ratio of that as water to orange. And the ratio is going to be 3 to 1. 3 compared to 1. So what that means is for every 3 bits of water you put in your glass, you need to put 1 bit of orange. So at the moment, I haven't said how much water you're going to put in or how much orange. I haven't done any measurements, but I've said for every 3 bits of water, there's 1 bit of orange, or for every 1 bit of orange, there's 3 bits of water. So if we first of all said, I'm going to put in 10 milliliters of orange, wow, we know to get from 1 to 10, all we've done is multiply that by 10. And the rule here, as it was when we did fractions before, is whatever you do with one side, you do with the other. So we multiply this side. So if we had 10 milliliters of orange, we would have to have 30 milliliters of water. Let's undo that and give another example. But let's do the other side. So this time, we're going to put in 60 milliliters of water. Well, to get from 3 to 60, we can times by 20. And again, whatever you do to one side, you do to the other. So that's times by 20 as well. 20 milliliters of orange. So if you had 60 milliliters of water, you put in 20 milliliters of orange. So relatively straightforward. Whatever you do to one side, if you've got measurements for one side of the calculation, whatever you do for that side, you have to do to the other, and to keep them in the same ratio. Slightly more difficult, rub this out, is when you're given a total amount. This never rubs out very well on the dots for some reason. I'll have to leave those dots on the screen. We're getting rid of some of them. No, it won't work at the dots, but we'll cope with those. So let's say that you're told that you have 1 litre of drink in total. So water and orange combined is 1 litre. Well, the first thing we want to know, just to make life a little bit easier for us, is 1 litre is the same as 1,000 millilitres. That will just make life a little bit easier for us shortly. If we think about our drink, that's meant to be a glass. It's split into 4 sections. Let's see if we can do some colours here. So my orange juice, we know we've got 1 of them. And we know for every 1 of orange, we've got 3 bits of water. So our drink is actually in 4 parts. 1 orange and 3 water. So if we've got 1 litre of drink, what we want to work out is how much is each part of that drink worth? Well, we know we've got 1,000 millilitres, and we've said it's in 4 sections, 4 parts. 1,000 divided by 4 is 250 millilitres. So that means every part we've got in our drink is worth 250 millilitres. We go back to our original ratio, which is 3 to 1. Well, if we've got 3 250 millilitres, that would equal 750. And if we've got 1 250 millilitre, that just equals 250. So our answer of, if we've got 1 litre of drink, we use 750 millilitres of water and 250 millilitres of orange. Danger that what often people do when they'll see this calculation, you've got 1,000 millilitres, how much water do you use? They'll see that there's 3 parts water, and they'll do 1,000 divided by 3. But obviously that's forgetting that you've got some orange juice in your glass as well. So the key is to think about, what is my total parts in altogether? Well, I've got 3 water and 1 orange, so it must be 4. So I've divided my 1,000 divided by 4. So far, and we'll only look today at 2. You could have more details. So to make a cocktail, non-alcoholic cocktail, it's called a Shirley Temple. Anybody's aware? You put in 3 bits of lemonade, you put in 1 bit of lime juice, and you put in half a bit of what's called grenadine. So the ratio here is actually 3 to 1 to a half. I don't usually like putting halves in, so I'm just going to double everything. So 6 to 1. So if we're making this cocktail, we've got 3 sections to it: our lemonade, our lime, and our grenadine, of a ratio of 6 to 2 to 1. Works exactly the same as the orange juice. So if I've got 60 millilitres of lemonade, I know I'm going to have 20 millilitres of lime and 10 millilitres of grenadine. If I've got 2 litres in total, I know I've got 6 add 2 add 1 is 9 parts. So I'll have to divide my total by 9 and then split it up equally amongst the amounts. So again, hopefully as you're looking at that makes sense, but it'll make more sense when you get to do a practice questions. Just go back to the slide. And all I've got on the slide here is to reiterate that. So the orange squash, we need a ratio of water to orange of 3 to 1. Key thing there to note, I've said the ratio of water to orange is 3 to 1. So that means water is 3 and orange is 1, because I've said the ratio is water to orange. If I'd said the ratio was orange to water, it'd be 1.3. It's always important to keep the ratio the same way round as you're expecting it. So if we use 10 millilitres of orange, we need to times the other side by 10. So that's 30 millilitres of water. If we use 60 millilitres of water, that's equivalent to 20 millilitres of orange. And if we have a litre in total, we split it into 4, giving us 750 mils of water and 250 mils of orange. Another thing we need to look at in terms of ratios, and again, this is very similar to fractions. So I know I've said this a few times, but if you didn't do the fractions webinar, this might be a good time to ask for it, and we'll send it afterwards and go through it. And this is called simplifying ratios. So let's say we have a school and it has a ratio of girls to boys of 180 to 120. And again, I've said the ratio is girls to boys, so it means 180 girls to 120 boys. That's the way the words are, so that's the way I've put the numbers. What we always want to try and do with maths, and certainly fractions I mentioned, and certainly with ratio, is we want to try and reduce the numbers down to the lowest possible factor that we can. And you'll see why in a moment. So if I look at both of these, I can see they're both ending in 0. So I know I can divide them both by 10. So if I divide 180 by 10, that'd give me 18. And if I divide 120 by 10, that'd give me 12. So my ratio of 180 to 120 is exactly the same ratio as 18 to 12. I can simplify that down again. I could halve it and then halve it again. There's various things. But looking, I can tell that 6 goes into both of those. So if I did 18 divided by 6 would give me 3. And 12 divided by 6 gives me 2. So my actual ratio for this school of girls to boys is 3 to 2. If we think about it practically, if you were imagining a school and how many girls and boys are there, imagine 160 girls and then 120 boys is very difficult to do. Imagining for every 3 girls, there's 2 boys. I can imagine that a little bit easier. It's a bit easier to imagine 5 people, of which 3 of them are girls and 2 of them are boys. So it's an easier ratio to work with. So again, in your test, you will probably get asked with a ratio to simplify to the lowest ratio, which is what we've done there. It may not even use those words. It may just say give the ratio, but it would expect you to simplify it down as far as possible. And all I've done is looked at something that's common to both. In the first case, both of them can be divided by 10. And in the second case, both of them can be divided by 6. I can't go any lower than 3 and 2 because there's nothing that goes into both of those numbers equally, apart from the number 1, but that just gives us 3 and 2 again, so we just keep going. So that's the lowest we can go. So you always want to try and get the simplifying down to, in fractions we call it lowest common denominator sometimes. In fractions, we just talk about going down to the simplest simplest ratio that you can. So that's simplifying down. You may also have to scale up. So let's take a workplace. And that I got a ratio of managers. Not very good writing on these words, I'm afraid. Managers to employees of 1 to 15. So what this means is for every 1 manager, there's 15 employees, or for every 15 employees, they have to have 1 manager. So if it says we know in this workplace there are 25 managers, well, to get from 1 to 25, all I've done is multiply by 25. So let's do the same with this side. And I'm not doing this in my head, but 15 times 25 equals 375 employees. So our actual figures here are 25 managers compared to 375 employees. Once again, I haven't written the word manager employees because at the top it tells me the ratio is manager to employees. So I know that's what each of these are. So our ratio of 1 to 15 actually gives us these actual figures. So previously we had the actual figures of the school kids and we reduced it down to the ratio. Here we were given the ratio and we've actually scaled it up to give us the actual figures. Going back to my presentation, and again, this is just reiterating what I said. We always want ratios in their simplest form because it helps us better understand them. So we've scaled down from 180 girls to 120 boys. That can be simplified down to 3 to 2 in the steps that I said before. Or we can expand, and we may need them to reflect the real numbers. So we know the ratio is 1 to 15, but what actually that means in this workplace is there are 25 managers and there are 375 employees. So we're scaling up, if you like. Final aspect of ratio that we're going to look at today is comparing ratios. And again, if I give another scenario, work through it, I hope that makes sense. Let's say you want to buy some green paint, and you may have seen in the hardware shops, they do this mixing thing. I think Dulux and some others do it, other brand names do it, where you can mix different colours to get a great shade. And let's say in this one shop, they have a paint called Paint A, and that is made of 4 parts blue paint, 6 parts yellow to make the green that you want. Slightly different mixture in a different shop with a different paint, and that uses 5 parts blue mixture to 7 parts yellow. The issue here is the yellow paint is really expensive, so you want to use as little yellow paint as you can because that will make your paint a little bit cheaper. The problem we've got is we can't compare these two because on one of them, we're only using 6 parts yellow, so it's less yellow. However, we don't get as much paint because there's only 4 parts blue. The other one, we get more paint because there's 5 parts and 7 parts, but there's more yellow, so that might be more expensive. So we're not able to compare these two things, so they're not looking at the same thing. So we need to find a way, some common factors to enable us to do that. So if I go to the whiteboard again. So we said that the 2 paints were, let's write up here so we remember the way around. They were blue to yellow is the ratio. And our paint A had a ratio of 4 blue to 6 yellow. And on this side, we had 5 blue to 7 yellow. And we want to compare them. What we need to do is we need one side of the ratios to be equal. because we can't compare 4 to 5 and we can't compare 6 to 7 because they're different ratios. Looking instinctively, I know that 4 can go into 20, and I know that 5 goes into 20. There's other figures as well, but 20 is a nice, easy figure to use. To get from 4 to 20, all we do is multiply by 5. So if we do that on one side, we need to do exactly the same on the other. As I've said throughout, whatever you do to one side, you have to do to the other. So 6 multiplied by 5 is 30. This side, to get from 5 to 20, we need to multiply by 4. And whatever we do to one side, we do to the other. 7 times 4 is 28. So now if we look at our calculations, both of them use 20 parts of blue paint. This one, however, only uses 28 parts of yellow, whereas the one over here uses 30 parts. So we said at the start the yellow paint was really expensive. So I want to buy this one because for the same amount of paint, because I'm using 20 parts blue, I'm using less yellow in the ratio, so I'm getting a better return on shop B. So by being able to compare the 20 figures, we've now made it equal, so we can actually compare our other one, and we know that paint B uses less yellow for the amount of blue it does. At no point have I said how much paint we're using. I'm not said whether we made half a tin or a litre or 10 litres or a bath full or whatever. It doesn't matter how much paint we're using. We just know that if we buy 20 blue over here, we're going to have to buy 30 lots of yellow. Here, if we buy 20 blue, we're going to have to buy 28 blocks of yellow. So this one has got to be more economical if the yellow is expensive. Just to prove the point, we've got some numbers. So what I've gone through today is to look at what probability is and how to calculate it. And the key with probability is that it's the number of ways something can happen. So how many ways can I get 3 on the dice over the total number of possibilities? In that case, how many numbers are there on the dice? We usually write probability as a fraction, as a decimal, or as a percentage. In the test, if the question asks you for one of those, that's what you do. If not, you can choose. And we've also produced probability lines and probability trees. Probability lines are a good way of representing probability. Probability trees are a good way of you working out what are combined events or multiple events. With ratio, we talked about what it is, and it's one number related to another. We were given amounts. So we had 1 litre of orange squash, and we could work out from the ratio. And similarly, if we were given the ratio, we could then work out how many employees there were in the workplace, for example. And at the end there, we've gone through simplifying, expanding, and comparing ratios. One thing I haven't gone through on purpose that relates to ratios is money. One of the key things you often get with ratios is exchanging money. So £1 is worth $1.2. I don't know what the exchange rate is. So we haven't done that. And the other thing is maps, where on a map, the scale of a map is 1 to 10,000. I haven't done those because the next webinar we're doing on math in a couple of weeks is about measures. And so I'll cover those in there because they come better under that topic. They are related to ratios, but they're particularly looking at measures of money and distance in those ways. So quite a bit in this one. My personal view is probability and ratio isn't the most difficult topic to look at. That's very easy for me to say. But once you've done it, it's actually relatively straightforward. There isn't a lot of maths that you do. The calculations are relatively straightforward. It's knowing what's the right calculation to do at the right time. But hopefully on the back of this, any questions you've got and then any follow-up work we do in terms of questions, hopefully that will make it clearer. So thank you very much for listening. And are there any questions?